Okay, hi everybody. May I ask to turn on your camera, please? Thanks, no. Others, please join. Okay, thanks. The plan, as you know, today is to continue discussion about the pipelining. Hopefully, we reach a good point. Probably we cannot finish pipelining today. We may need next Tuesday as well for this. But before we start, do you have any question for me that you want to ask? And these questions, again, it will be good beyond the topic of computer architecture that we discussed. I mean, the technical aspect. I would be happy to discuss like more, even for those who are interested beyond some research topic, more advanced for those who are interested to do research in computer architecture or relevant aspect of computer architecture, which I mentioned could be about machine learning, AI, which has a computer architecture flavor. I'm happy to discuss, and these are also important for some of you who are interested to do graduate studies later on after you graduated. And also, if you are not sure at this point if you want to do graduate study anyway, that would be a good opportunity to discuss any ideas, any insight that you may want to share with others. This is a good opportunity to discuss and bring it up so others can also learn about this. Again, this is important. Some of these topics are really important, and even though like in this course we mainly talk about the fundamentals, and that's because they are important. In later on, if you get the chance to take some of the advanced courses related to computer architecture, you may learn more about some state-of-the-art topics, computer architecture, beyond these fundamentals. But still, you should know that many researchers still working on even some of these fundamentals and making and not only in research but also several companies, chip makers, still working on like building chips based on these ideas, these fundamental ideas. So it's very important to learn about this, and some of you may also interested into get into the practice of like building stuff. So make sure that you use this opportunity to go beyond what we discuss in this course, and if you want to discuss something, share something with others, I would definitely encourage that. Not only here in the class, but also I would be happy to set up any discussions, extra kind of beyond this time, some other times, and also after your class has finished, please feel free to contact me anytime. At this point, I'm sure you know, you are now familiar with the style, with my style, not only teaching, but also if you look at some of the research that we do in my lab, I would be happy to discuss research opportunities with you later on after you're done. And if some of you are also interested in getting into research, I have some research opportunities over summer. If for those who are really interested in the intersection of AI, ML, and computer architecture, and you are doing very well in this course, and you think that if you are interested in research, please feel free to drop me an email. I plan to hire a couple of students, undergraduate students, over the summer, doing research. Yeah, please keep in touch. There are lots of very interesting work going on at this intersection, and I highly encourage that, especially for those who are highly motivated, and also specifically, I have some criteria when it comes to engaging students, especially like for these opportunities. I would encourage those of you who are coming from, especially in computer science, like I see way less number of like female students, those who are coming from underrepresented groups. I would definitely encourage those, keep in touch, and I would be happy to discuss research opportunities. So keep in this in your mind, and think about it, and but also look into some of the research that we do. Okay, let's start. So if you remember, we discussed about some of we contrasted and discussed some of the issues. Somehow you have clear motivation why pipelining might be a good opportunity to improve performance, because obviously it increases the parallel execution of multiple different instruction. So in an abstract way, if you think about it, we have some resources, and think about this like stuff as these hardware, these gates as some resources we do want to share. Somehow, one way that we approach sharing, and like whenever it comes to all of these ideas, not only pipelining, other idea for performance improvement, it's really simple, right? We have some resources. We somehow want to find a creative way to share these resources with like multiple different instruction or activity that we do. And you can make a very clear correspondence with beyond this computer architecture, like in life, the activity that you do, like we discuss about this laundry, right? This is one of the activity in life. We have some resources, we want to do laundry, let's do some resource sharing. Not only laundry, but also many other things, right? So you have some resources, you want to use these resources to do things, how you can make it faster. Let's do resource sharing. And in also like the other courses that some of you may have taken or will take later on is OS, operating system, right? There also you have like some resources. You want to come up with some creative idea to share resources, some algorithms that enable you to make these share resources, but also you think hard to make this resource sharing with some criteria to make it fair for all activities, or you want to like have some good strategies, right, in order to get the best. Because like, for example, you have heterogeneous type of activities. Some activities are longer, some activities are much shorter. How you assign resources to these activities to gain the best performance, and there is not a single solution for this, right? There might be many different ways of assigning these tasks to resources. Like one strategy is to whoever comes first, like assign it to the resource, but not necessarily that this comes to the best result. Sometimes maybe some strategy would say, okay, assign the resources to those activities that need the resources the least, right? So the small task first, right? This is another strategy. One other strategy is assign resources to the largest task. Yet another strategy. We have like, you can think about many different ways of doing this scheduling, right? And this is somehow a scheduling problem in abstract way. So like think of, when we discuss this, make correspondence to this and think about it, because this gives you some clear insight, and you can make it not only clear insight, maybe you might have some idea, come up with new idea, but also make a best sense out of these ideas, why they make sense and why these are important, and we discuss things. Okay. So if you remember, when we discussed multi-cycle, we somehow added some resources, some new hardware in order to carry information for us from one step to the next, right? So we added some new hardware here, right? So when we fetch instruction, right, at the end we want to store it in that single cycle in the first cycle, because next cycle we need to use it to to decode it, right, or to do some ALU operation, and each of these happens in different cycles, right? So if we don't store it, we lose information. And next cycle, we need to get these data, right? So that was this adding cycle, this adding new hardware, obviously was needed. Here in pipelining, we need those, but also these new hardware needs to carry more information for us, not only the result of previous cycle, like for example, not only the instruction that we fetched, But also we need more than that. Why? Because once we are done with this, later on in later stages, for example, if we don't carry those new information, if we need something else, like for example, say we are doing some ALU stuff, right? And one other instruction, like some other instruction has entered the pipeline and changed the PC, obviously, right? And later on, if we want to, because we need to increment the PC, right? We already lost that information. So, we here in pipeline, in pipelining, in the new hardware that we are designing, we need to carry more information, because the whole infrastructure, the whole hardware will be used by some other instruction. Other instruction will change the states, the architectural state, right? While we are not done with this current instruction. But in multi-cycle, if you think about it, we basically we had this opportunity, even though it was clearly waste of resources. We had this opportunity to not be worried about like somebody else writes somewhere that later on we need it, right? So we finish each instruction. Once the instruction is finished, we start the second instruction, the third instruction, and so on. So we did not need to worry about like losing some information while we are not done with the current instruction, right? So that's somehow the difference, and that's the thing you need to consider here. So as a result, so not only we need to carry like the instruction, like for example here in the after we fetch, but we also need to carry this PC +4, right? Because somebody else will write into PC. Maybe the next instruction is a jump or something, right? So we need to carry this, right? PC +4 here, and also the next one when we are decoding and executing, right? And all of these information that are needed. So all information that has been retrieved in the decoding, because we obviously need it in execution, and also and so on. So that's somehow a difference with respect to multi-cycle architecture that we have discussed. And one other thing is important to think about it is no resource is used by more than one stage, right? So obviously we cannot share. We are not able to share the same resource for more than a stage, right? So once we are making use of one hardware in one stage, right, we cannot like use the same resources. Like we cannot use the ALU for doing something else, right? Because this is one resource. We cannot share it with some others, right? In here in this execution. Okay, let's look at some maybe examples, right? So here load word, right? So we fetch the instruction for load word. Hopefully you remember the semantic of load word, and then we decode the instruction. So obviously some information is retrieved, and then we do an execution using the ALU. And then we access the memory because we need to read from the memory, and then we need to write the content, the value of the memory in the address that was specified in the load word, and write it back to the corresponding register. So that's what happening for load word. But also, if you think about it, like here in this execution paradigm, all instruction, no matter what, no matter it is load word, store word, jump, right, needs to follow the same path, right? And obviously, right away you should think, wait a minute, like, isn't it a restriction if they all need to follow the same path? Because maybe not all instructions needed all of these resources, right? So for example, say like jump, okay? Does jump need like, say, register or memory? No, right? So, but it needs to go through all paths, right? So, or you saw this some other instruction like may not need to have access to do any ALU, because like say like even like our instructions, right, do not need to have access to the memory, right? They don't write to the memory or read from memory. So some of the instruction, even some instruction classes like R types, do not need one particular stage, but no matter what, they need to follow the same pipeline stages as soon as we decide about these stages, because it's a pipeline. We cannot make an exception. Somehow pipeline, like everything should go through the same pipeline. There is no exception. Everything treated the same way. So this seems a kind of restriction, right? If you think about it, because there are obviously different type of instruction that require different resources. Okay.
Excuse me, Professor. I just had a quick question.
Sure.
So regarding the pipelining, how we have half of the register file, we have the read inputs and the data outputs as part of the instruction decode, but we don't have the register write and write data as part of the decode. How do we handle that if they're on the same unit? I just thought about that question during the last slide.
Can you please repeat that again?
Sure. So we have our register file unit, kind of our device, and the instruction decode step. How do we handle the write register and write data part of that if that's part of a separate part of our pipeline? If we have that whole unit, the register process, like the register file unit, as a separate part of our pipeline? Do we control our register with multiple different pipeline signals at once?
Good point. Good point. And we'll discuss about it. Like this is obviously a very perfect point, because obviously a bottleneck here, right? So we need register during different stages, because obviously we need register during decoding, right? Like this stage, right? For reading stuff, and later on we again need register, right, in writing. So we need like same resource but different stages, right? So this is a bottleneck that can be a problematic thing, but there are solutions for that. Like one solution is say maybe we want to make sure that reading happens, because we have one cycle for that. Maybe we want to like to read first, make sure that we read first before writing things, right? If we have like if we are using the same register, right, in two different instructions, because obviously we don't have unlimited number of registers, right? If we had unlimited number of registers, we could somehow like assign like totally different register in instruction. Like this can be handled by compiler, but we don't have it, and we need to find an intelligent way in order to coordinate stuff, to make sure that like we do not make things, we do not make any inconsistent execution, right? We do not make incorrect result, because if we write to a register, imagine that like we write to a register in one stage before even like reading from that register for some other instruction, then things could go wrong, right? That was a good point Noah mentioned. So there are solutions for that, and we'll discuss some of those solutions. Right. Okay. So this is an example of like again, very simple example of a pipeline where two instructions are like entering the stages, like load word and later on stop, right? So two independent instructions, in this case, load word, like we want to access the memory and load something, put it into a register, and in stop we do a R-type ALU operation, right? So they enter the pipeline. So in here, we first obviously we need to fetch the instruction load word. We cannot, as you know, we cannot do anything for stop because we need to first fetch the first instruction. Okay, and obviously we cannot fetch both of sub and load word at the same time, because obviously we discussed that these dependencies, right? We cannot use the same pipeline, right? The same stage for two instruction at a time, right? So And load word need to get executed first because it comes first, right? This is like identified by the compiler, and like we need to obey this dependency, right? Load word first, right? So this is the ordering of these two instructions. So load word fetched. Once load word fetched, it can go to decoding stage, and then we can fetch sub, and then sequentially load word goes for execution. We can do sub instruction, decode sub instruction. Next, we load word goes for memory access because it needs to read from the memory. Okay, and sub could use ALU for doing subtraction of these two register, right? 2 and 3, right? And you know, by definition, then the result needs to be written to register number 11. And then we can move the load word to write back. Needs to write back the content of the memory that has been read into the register, and then sub is moving to memory access. And obviously you clearly see that, like here sub, does it need memory access? Does sub need any memory access here?
No, it does not.
It does not, right? But
because you store it back in a register.
Yeah, like it does nothing here, right? So it seems that like wasting a resource here, right? It needs to definitely go through this. Like we cannot like move it to write back because now write back is doing is executing load word, right? So it stays there. Maybe some other like instruction could use this, but like apparently we cannot like do anything with it because all instruction needs to go through the same pipeline. Like there's no exception. Like once you enter, you should make sure that you move forward and go through the whole pipeline, no matter what, until you finished. So there are some resource waste here, and then sub can write back the result into register number 11, and it's done, right? Even though things could go wrong even further than this, I mean, here there was no major issue. It was just wasting one state resources memory for like sub, which was nothing to do. But as Noah mentioned, maybe like could be worse, like writing result into a register where could make things more complicated. Using the same resources, somehow we needed something more than this. Like we needed new thing to handle this. Somehow we need extra stuff to handle these situations. This is illustrating pipeline from operation view, right? So the first instruction is instruction 0, fetch, decode, execute. By instruction 1, also at T1, fetched, T2 decode and execute, T3 and so on. Instruction 2 at T2 fetched and so on, and then at T4 we reach this state that is full with the whole pipeline is full, right? So the fetch state is executing instruction 4, decoding is executing instruction 3. The execution is doing instruction 2, memory is doing instruction 1, and writing back is doing instruction 0, right? At T4. At T4, basically the whole pipeline is like beautifully filled with like 5 different instructions, right? And from now on, T4 until the end of program, if like in an ideal case, like we utilize in ideal case where like no like dependency, no unusual thing, like we have full utilization of the pipeline until we are done, which is perfect, right? We somehow reach this steady state where the full pipeline is engaged doing something, which is great. And also this is like yet another view, like this one was operation view. This is resource view where the rows are the resources that we have these pipeline stages where at T0 it's busy with instruction 0, at T1 is busy with the first fetch is I1 and decoding in I0 and so on until we reach the steady state at T4, and this will go on until we are done. So this is like the same thing in 2 different view, right? So this is the resource view where the rows are resources, and this is the operation view, the rows are instructions, right? So like 2 different representation of the same thing, and this is important to think about it, and like sometimes maybe one view is more useful than the other view, and your computer scientist, like you should be aware of this different representation of showing the same concept for different purposes. Maybe there are some advantage for some work, some algorithmic or some analysis based on one view rather than the other one. Okay. Any question until here? Good. So now we need to also talk about the control signal. How about the control signal? Because control signals are also important, right? In single cycle, we were not worried about control signals because like we could generate the control signal beforehand, right? So like at like the control signal obviously could, once we know once we decode the instruction, right, we could generate the whole control signal right away, right? So generating this control signal, I will discuss about it, like we discuss about like this logic that could somehow generate the control signal for us. Is there any question? So Eric is asking, you only had one instruction, so one set of control signal per instruction. That's right. So yes, good point, Eric. Yeah, we have one instruction. We did not need to be worried about like at some point we are like in the steady state, we are like having totally different instructions at different stage, right? Like, wow, how we handle this. Things could go wrong in like single cycle. Like once we are done with one instruction, we can execute the next, and like we could decide about the whole control signal, about the current instruction once we know the instruction. So things could not go wrong, and things would be easy in single cycle, but we need extra thing. We need to figure out how to generate control signal for basically pipelining. And would the control signal have to peak at every instruction currently in the pipeline and generate control signal based off that? Let me think. I have to peak at every instruction currently in the pipeline. Yes, but there are different strategies that. Yes, good point. Remember, yes, we need to have a way to remember things. Very good word for using that, right? So because like at some point, once we know the instruction, we obviously like single cycle, we can like generate the whole signal, control signal right away, right? But we need a way to send the signal whenever it is needed, right? Or in a way, you use a good word, remember things, or I would say carry over signals. One way is carrying over, but also we could, at each state, we could also regenerate this control signal. Like one strategy is to, we have a slide actually for this. So one strategy is to decode, right, in pretty much like single cycle, right? Because once we have the instruction, we could like generate the whole control signal, as you know, in single cycle for the whole stages, right? We know exactly like how to generate this, and we can generate it right away. One strategy that Eric beautifully mentioned is to, why not generating the whole thing and remember things, right? This is a very valid point, right? So we generate and we keep track of things, right? So we, in the execution, like we need all of this. Obviously we need to remember or store what we need in execution, memory access, and writing back, right? So in here, and then next, once we execute it, yeah, we execute it. Like we don't need to like keep this anymore, but we need to keep memory access and write back control signals, right? So we carry it over here. Once we are done with memory access, then like we don't care, but we still need to carry over or remember or store control signal for writing back, right? Because otherwise, like, wow, like what was the instruction? what was the control signal I need to have for each stage. One other idea is to rather than remembering, like probably this is a strategy of somebody like me that have a weak memory, like trying to generate the signal whenever I need, right? So whenever I need a signal, okay, what was the instruction, right? So how I generate, okay, yeah, I know how to generate, but I don't want to remember it, right? But obviously I need to do extra work. I need to do generation of the signal whenever I need it, right? So I obviously need to do some brain work to do this. So in the hardware, we need some combinational logic to do this at every stage, right? Whenever we needed it. Which one is better? Like, again, trade-off. Is this clear for you? I'm asking all of you. I think it should be very clear for Eric, right? And thanks for mentioning it. Yeah, I like the remember word. I like it. So it's definitely a good word to use here. So again, like one generating once using some storage. Again, for storing, like we need to make these this hardware sequential logic part, which needs to store the result larger, obviously, to store this signal that has been generated once the instruction is decoded, and then carrying over or remember it over multiple stages. One other is to use combinational logic to every time like generate things rather than or decode it rather than, and probably decode locally is a good word here too, because every time that we need to generate something, we do it locally for the current task at hand, right? So if we do it like here at the memory access, you only need to decode relevant part of this, right? So we don't need to decode the whole thing, right? We need to decode the contour signals for the current memory access, right? That we needed. Obviously, we need to like do this right before we needed it, right? So we cannot do this same at the same cycle, because just wasting is, we need to do right before it, right before the next cycle. And this is how it looks like in the whole pipeline, right? So we have some extra storage here to once we generate them, once we decode them, to the store. And here you see that, for example, this execution part is used here to send the right signal to ALU control for doing the right ALU operation here that we need. This memory part will be carried over here and is not used in this stage at all, also the memory write back. So these two obviously like just carry over. But this execution signal, you see, like main part is deciding about this ALU operation, but some other also like sending it to this mux, because we need to like find the right input to send to the ALU, and also this guy, this other mux that needs decide to carry over to the next stage, right? And then during the this stage, the write back stuff will be carried over next, but the memory access, we need to know what memory we need to get access, or write or read. You see two different control signals for write or read. If we have like two different ports for write or read. Sometimes, like if we have one port for both read or write, that looks different, right? So basically, you remember this example that we had one port was either like whether it's right or not. If it's not right, meaning that it's reading from the memory. And that's obviously like here in this case, like two different, but there is like one bit determining whether we want to write or not. Not writing meaning reading, okay? So you know about this. And also if this is a branching stuff, right? And the next one, which we need this write back control signal that control this marks, right? And also send the right signal for register write when we want to, because we want to write to the correct register. So this control signal, right? You see that it was generated in the coding stage, but was carried over all the way to the last stage when we needed it, right? So it travels a long path, a long time. It's just carried over.
So this was for the first control type you mentioned on the slide before that. Because there were the two different options. This was for option one.
Yes. Yep. Yes. And this is another kind of, you see the correspondence to single cycle, right? In top, you see the microarchitecture for single cycle. You see it like less hardware stuff, right? Is simpler, obviously, less resources, but you already have a clear picture like about the shortcoming of single cycle performance stuff. Pipelining, we obviously did extra stuff. In between, we have multiple stages, but we know about the benefit of it, at least until now. And right, so this is also the case when when we might engage, or we might need the same resource register file at the same time, that we'll discuss later on how to handle that. Is there any question? Okay, would the combinational logic be a slowdown? Be a slowdown due to a large number of permutation of instructions. Yeah, that's a good point that you mentioned. Basically, it is, and you know that like any combination logic doesn't come not only the cost of the hardware, but also is not zero in terms of execution time, right? So every time that we need something, we need to execute it, and it takes time, right? Okay. You also have 1/4 of the time to find the control signal for instruction unless future instruction be preloaded. Yes, yes. Okay. Yeah, this is also another viewpoint of like remembering stuff whenever it is needed, carrying over the information. So the goal is to, as you remember, right, increase the throughput with little increase in cost. Because we know that, like, at the end, we need to pay some cost, but hopefully as least as possible. So we need to we need to somehow avoid some of the shortcomings that we had previously, right? So if you remember, so we needed to avoid repetition of identical operation, right? And also we needed to avoid the repetition of independent operation. So or basically, in a way, we needed to make sure that like the operation that comes to the pipeline are independent, right? Otherwise, if they are dependent, we cannot process them at the same time, and we need to have this property of having a non-uniform partitioning was bad idea, because at the end of the day we have same clock cycle, and if the stages are not uniform, somewhere we lose some utilization. So some of these stages may not be engaged fully. And you remember these examples that we had in previous slides. So there it is. Yeah, here. Come on. Yeah. So here, like if they are not uniform, see here, for example, like some stages for some instructions, since they are not uniform, we are not fully using these resources here, or wasting some resources here. Even though like we have 200 picosecond assigned to this stage, but it's not using the resources fully, and we cannot like doing something else there to fill this gap. So we are moving further away from ideal case where everything is fitted perfectly at each stage. So we we are happy that we fully utilize the resources and we wasted nothing. But this doesn't come without any uniform assignment. So this is the ideal case where we have uniform partitioning of sub operations, so we can process evenly these sub operations that do not share resources. Okay, so these three properties are important, right? So repetition of identical operation, repetition of independent operation. So we shouldn't have any dependency between operations. And the first one is like we need to like pass through whole pipeline. We cannot skip some stages. And we need to have uniform partition. But it turns out that like none of these properties, these good properties that we want, are even met in the case of pipelining, right? At least with the current solution that we have discussed. So we have different instruction, as just discussed in the example, in the sub case. Not all needs the same stages. Like in sub, we didn't need the memory access because we simply didn't need that. So it doesn't satisfy this identical operation things, where we need to force different instruction to go through the same pipeline stages, which makes it fragmented. So we have, as a result, we get some external fragmentation, or in other way, some pipeline stages would be idle, doing nothing for some instruction. This is called external fragmentation. And we do not even also get uniform sub-operation because different pipeline stages do not have the same latency, as you know, as we just discussed, right? So we somehow, since we are bounded by this, because we assign the same, because like we cannot have different cycle time, right? This is fixed, right? Cycle time is fixed, and we are bounded by that. So forcing each stage to be controlled by the same clock, right? Yeah, we could like have multiple clocks, right, to assign to different stages, but we are not doing that. So internal fragmentation as a result will happen. So some stages require different time. The ideal case was that each state exactly required the same time, so it could fill the gap perfectly. And instructions are not independent of each other. We need to detect and resolve these inter-instruction dependencies to make sure that, say, whenever we want to write the result, we do not mess with the content of the register that may be needed for some other instruction that are not fully done yet. So basically, sometimes these pipeline stalls happen, which avoid the pipeline to move forward in a perfect way, right? In a perfect way, perfect scenario is the scenario where like things move forward perfectly, smoothly, in other way. Like once it is in the steady state, like the pipeline would stay in the steady state like until your program has been finished. But this is ideal, and like we cannot achieve all of these three properties, important properties, or in a way ideal properties that we want to achieve. And by the way, like these are again, like if you think about it, these properties are not only for like macro architecture stuff. Like for other example, if you think about it, like even for laundry, should be are important, right? So these are ideal if like having the identical operation, right? So all needs to go through the same, like even for laundry, some of the clauses, maybe you do not want them to you do not want to use like dryer, right? For some reason, at least I don't use for some clothes, right? You do not have uniform sub operation, right? As we discussed, like dryer takes way more time than other, and independent operation also. I mean, in drying, like all of them are independent, but you can come up with the example that this needs to be carefully thought and planned for it in order to make sure that these are not using the same hardware, and things cannot go wrong if we have not thought about it. So basically, as a result, we need this property to be taken care of. Basically, these properties to make sure that the pipeline stages are balanced, basically are fully engaged in a perfect way, keeping the pipeline correct and moving. We don't mess with the dependency, like we handle the data dependency, control dependencies. This example that we mentioned, register, was like an example of data dependency, but we have some other dependencies. Was example of resource contention, the second one. But we have some other dependencies like control dependencies, and also we need to handle long latency operation as well. Like some operation takes more time, say like we have a stage of memory access. Obviously this takes way more time than like using ALU. And we have some other exception, like interrupts needs to be handled, and we need to minimize the stalls. That we will discuss about some strategy to take care of these things next. But let's stop here. I would stay here for a few minutes if you have any questions. Otherwise, have a fantastic weekend and enjoy.
Hey, I have kind of an off-topic question.
Absolutely.
So you said earlier that this class is good for like artificial intelligence.
This class would be good for artificial intelligence.
Or like computer architecture is like good to know for artificial intelligence.
Yes, but like let's discuss it. Like it's good for building AI systems. for algorithmic part of AI, you don't need to know computer architecture at all, because like AI has different aspects, AI or machine learning, right? So, or has several different aspects, right? But let's think about it like at a more high level. Like in AI, we need obviously some algorithms, right? So we need to have like planning algorithms, reinforcement learning, search. All of these are part of AI. For like, say, for search, do we need computer architecture? No. Why we need, like, it's the algorithmic part. But when it comes to building a system, AI system, a machine learning system, and by this I mean like a system that is operational, not necessarily the whole part of the system needs to be machine learning involved, but when it comes to, when we say machine learning system or AI system, some components in the whole system is basically running some AI algorithms. Say, for example, Google running some advertisements, right? So their advertisement system is a machine learning system. Or Amazon is running recommendation system for recommending products, right? So obviously they run some ML algorithm for recommendation. And this is not only AI or machine learning, is AI or machine learning systems. And of course, very important part of this is computer architecture.
Okay.
And computer architecture is very important part of ML system when it comes to large scale deployment. I can maybe even share a paper on this. So
Oh, that'd be good.
you can take a look about recommendation system and computer architecture coming out of Facebook.
Thank you.
Sure. Let me find it. So.
Do you ever think computers are gonna be like us one day, or is that all just in the movies?
I have my own opinion, but maybe to be fair, I have also a very good recommendation for that. I can send you a documentary. You can maybe watch
Oh,
it.
that'd be awesome.
Watch
I
it.
love documentaries.
Yeah, this is one of the paper you can take a look. It involves a lot of computer architecture. It's called Deep Praxis, but there was another also.
Do you ever think we can insert emotions into a computer, or is that just kind of like impossible?
Good
That's kind
point.
of unnecessary.
I mean, it's not probably necessary.
Like, what if there's a way to make emotions allow computers to work faster? Kind of like how it works for humans. Like when someone gets mad, they're like stronger or something like that. I don't know.
Good point. Good point. Yeah. I mean, not. So think about it. Like many people believe that the consciousness comes from is computational, right? Some people also do not believe that, right? So if consciousness And as a result, emotion could be computational. Yeah, like we could get them in computer, right? We could build system that show emotion. I mean, like obviously, like you can emulate emotion, you know, in a artificial way, as the way how some of the current system they do, but currently they don't feel the emotion, right? But at some stage, I'm sure we reach the point that really computers or AI systems, robots essentially, feel the emotion too. But as one of the great AI scientists said also in this documentary, you will hear from him, maybe if we will reach this state, but maybe you don't want to marry the robot, right? Or you don't want your kids to marry to the robots when we have that. But for sure, we will reach that point, right?
Yeah, I hope people don't try and do that in the future. That'd be just kind of like weird.
Yeah, let me find this documentary. This is a fantastic one.
Like you saw that movie that was the dude fell in love with his cell phone or something? Siri?
Yeah, her.
Oh, wow. Oh yeah. I was like,
That was a good one. Yeah, that was certainly a good one that I do remember it. It was.
hey, have you seen The Social Network? That one was incredible.
Yes, Social Network was also a very good one. I like that when I watch it. Yeah.
I've watched that movie like probably 5 times.
Really?
Yeah, I'm just like so like it was like he got so lucky, but I feel like it was more of like the time he grew up in, like allowed him to like pretty much make a monopoly.
Yeah, but what aspect of it you liked?
I like how he made a website and then everyone uses it. Like like I thought it was a little unfair of how he kind of like stole his friend's idea, but he did make it like all by himself, and that's pretty crazy. Like,
Yeah, that's right. Let me first send it to you. Maybe I can also. This is the link to the documentary, and let me also show you this part, which was incredible.
it makes me think of like what we haven't created yet versus what we could and create our own monopolies, you know?
That's right. Yeah, yeah, yeah.
I think about that all the time.
Really?
Really, I kind of always kind of just invented ideas. I don't really carry through with most of them, but I did do a science fair project on one, and that was fun. Yeah, I messed with Peltier modules, and it was very fun.
Nice. Let me find this interesting point in this documentary. I love like this is like old. Some of these interviews are really old, like many years ago. And oh, I found it. Let me share it. Let me share it. Where is this? Do you see it?
Yeah, it's right there.
Now, machines can't write whether we should be able to.
Let me,
which is
because like this is some quick. interview, like some statement from 3 different scientists, and like these statements are different, and you can, I mean, I have my own opinion, like which one I do agree, and like you clearly see that, like how the AI turns out to be, and how the current version of AI is different from this perspective. Here, this
today can think. I have a basic question, which is, do these machines produce anything really new? When you consider the great new ideas produced by men like Newton and Darwin and Galileo, you'll find that initially they had to throw away the old rules that they've been brought up with. Now machines do what they've been told to do. They obey the rules that have been fed into them by man. And we know of no machines at present which have means of overcoming this limitation.
I have little doubt that we'll be able to produce machines and computer programs that will behave in a fashion that we speak of as intelligent, that these will be of great aid to man in terms of relieving him of intellectual work that is not fit for human production. Where my doubt comes in is whether we shall be able to produce machines and machine programs that are capable of creative thinking. I doubt very much, with the usual type of human vanity, that any artificial information processing system will ever be able to do this kind of inventive things. I rather doubt whether it's going to be possible to do this in our lifetime.
I'm convinced that machines can think.
Like this professor opinion, like totally wrong, right? It turns out to be that now we have machine that like can generate some creative things, right? Art, like even like poets, right? Interesting poems, poetry, right? Lot of creative things that we could not even imagine, but now it is out there, right? We have evidence for this. But listen to this, Oliver Selfridge, right? Like, and by the way, these, have you heard about Marvin Minsky, MIT?
I'm not sure.
They were both at the same time. This guy, like, listen to him.
I don't mean the machines will behave like men. I don't think for a very long time we're going to have a difficult problem distinguishing a man from a robot. And I don't think my daughter will ever marry a computer. But I think that computers will be doing the things that men do when we say they're thinking. Now, machines can't write good poetry or produce deathless music yet, but I don't see any stumbling block in a line of progress which will enable them to in the long run. I'm convinced that machines can and will think in our lifetime.
See? Is anything credible?
Wow.
This guy, you know, predicted something that turned out to be somehow, I mean, like we don't have a thinking machine yet, but like we have machine that can do some creative things, right?
It makes me think like in the future, people are going to be buying robot wives and stuff.
Yeah, why not?
Anna, this is amazing, but this just made me think of something. He said machines can't abandon what we give them. And I realized after taking this class and everything that it's completely possible to build a computer that can edit its own hardware.
Yes, that's...
And implement the AI into that. You would just have to have 2 hardwares and have it being able to transfer to one. Well, fixes the other with manufacture, like the equipment we use in assembly lines, and being able to flip between the 2. And in essence, completely be able to rebuild itself with its own AI system.
Yes, that's a perfect, fantastic idea. And yes, we don't have it, but at some point, imagine if AI system are able to do that, like they able to regenerate themselves, right? independent from us as a human, and then like
That's when the world ends.
That's when all our ethical issues become the word, like
yeah, I knew
that'd be
you thought
concerning.
about it, but you know, let's not be worried about the bad stuff that might happen in the future, right? Let's think about the possibilities, right? Doing incredible work. If we
That's also when world hunger ends too.
yeah, if we let's say, because of I don't think because of robots, AI will basically make us as a human distinct, but maybe because of nature or events, right? But let's imagine if that happens, right? If we and build such things, then our generation could continue in other forms, right? As close as to us, right? So they could go and also to other planets and survive and stuff and regenerate in this sense, right?
Yeah, there's definitely aliens out there. Like somewhere, there's another life form somewhere.
Yeah, and maybe these robots will find them, right? but this is fantastic idea that you mentioned, and this was actually not to this extent, but a version of this idea, way more limited. By somehow I call this synthesizing hardware. I thought about this idea of synthesizing hardware to some extent, which most aspect of it were fully automated by some AI algorithm, for example, the whole, for example, synthesizing the microarchitecture stuff, and even coming up with the new instructions that could make the hardware more efficient. Somehow synthesizing new machines for the right workload automatically, right? I've been thinking about this, it was last year. I've been thinking about it, but this is very limited than the idea that you mentioned. And this is great. And
I was kind of thinking the same thing of just kind of like the way we have a good construct of teaching AI things and then being able to implement that. And so after taking this class, you can kind of do a similar thing to it and teach it what its parts do and let it explore on its own and take data from entries.
Yes, exactly. And that's very much possible. Even it's difficult because human are heavily involved in designing hardware, designing architecture, right? And that's why architects think that there are architects who work in Intel, these large company nowadays, architects work in many of these companies. Even Facebook, they're building their own hardware, Apple building their own hardware, Google, all of this, right? We think that we are only able, and at the moment really it really requires some critical thinking, building, evaluation, validating, and making sure that it is efficient. But I don't see any reason why computers would not be able to do the same things even better, right? Maybe computers are able to find way more efficient, architecture, right, across different layers in the stack, right? I mean, we are working on, for example, if you think about the whole stack, people are working on synthesizing programs at the software level, right? But if we extend that into the hardware, and also if we extend that across the stack, right? So things work in coordination with each other across the stack, then we fully synthesize the whole system, like software, hardware, all of this, right?
That's what makes it such a scary thought. It would really just crash the economy, because then right now we're already having an issue with robotics taking over jobs. If someone developed something like that, it would pose a threat to jobs that people are really striving for, which is going into computer jobs, going into programming and development.
We're just gonna have to teach them all how to use a laptop.
Well, we're already trying to do that, but if a robot like that comes out, it would threaten that, because it could be mass produced then if it's developed.
Yeah. I mean, but I mean, even though like there are some concern about jobs, and you're absolutely right, then like we as a computer scientist, maybe we don't have a job, but like there would be yet another level that like human could contribute, right? So like at the end, we need to write a specification for this, like what system we want, right? Sometimes even like computers can think what system should be synthesized, right? You can like you can expect more from AI, right? Like until all jobs are gone, but obviously there would be new jobs, or at some point like we go and enjoy life. We don't need to do any work.
Yeah, I'm just glad it's not something that can be developed instantly. Even if you pursued this today, or someone did, it would take a long time and a lot of data and effort to make it. It's not a magical solution.
Yeah, it is not. And I mean, these are ideas that we discussed takes like, I'm sure, like decades. I mean, we are not anywhere close to these ideas. It takes decades.
So the key to a utopian future is AI.
Maybe, but I mean, there are like concern, even if we reach that state that we go and enjoy without needing to do any work, even like where like we have perfect things like robots doing very good work and like taking care of economy and everything, generating wealth for human, and we do enjoy, whether that's ideal life, people have argument about that, right? So we somehow need to work not only for generating wealth, but also human needs to work psychologically, right?
Oh, true.
And it would kind of mess with social class. Why would someone owning this robot earn more than someone owning that robot? Why would robots even be owned? There's a lot of opinions and philosophy to that.
Right. And but we are like, I feel that we are just at the beginning of like the huge revolution that will happen as a result of AI. It's just the beginning.
Yeah, a robot's gonna replace the dog as man's best friend.
But this is like, I would see it as an opportunity, all of this, even though like we have to be worried about concerns and everything, we have to be worried about all of these issues, especially I myself worried about this ethical aspect of AI, especially bias, fairness, all of this, which I teach in the ML course in 585, but this is like exciting. At least it's, especially you guys, you're the young generation, and the whole I mean, like if I'm kind of old, getting old, but you guys,
You're not that old. Come on.
I'm thinking, not really, like I'm thinking this all the time, like if I go back, if I were in your age, at your age, like at this time, wow, and that would be awesome. You know, doing a lot of incredible, at least having the opportunity to do a lot of incredible work, and you know,
We're gonna carry on your incredible work.
thanks. No, but like I wasted a lot of time in life, which I hope I did not. But anyway, I mean, you guys have, you should really should know that, right? You're in perfect situation, like in a ideal world, especially in a perfect country in the world. I grew up in Iran, and I mean it's different situation, right?
Wow.
You know, like in these countries, like it's life is not easy. It's difficult. So it's not ideal as it is here, right? So you guys should
Yeah, we got it made here.
should really see this as an opportunity, right? Is once we live only once, right? Make it perfect for yourself, especially at this time in the history. I'm sure that you guys could do some incredible work if you like think about it and like make the best out of it. It's perfect, and I hope I had this opportunity. I was at your age at this point. But
It's all right. They say everything happens for a reason.
yes. Yeah, but thanks for the discussion, and
Yes, sir. It was interesting. Thank you.
Thank you. I learned a bit more about AI and everything.
yeah, definitely you should, and try to read as much as possible, and discuss. I'm happy to discuss, and try to also engage in research, do some hands-on work to learn very closely, to do things in practice, go beyond like even what you learn in classes, and what like you expected. You were basically what are the expectation, like you can clearly get your degree easily, right? But go beyond this. Don't I mean, be ambitious as much as possible, because many things is possible, and go beyond the expectation, like do incredible work. This is what I can say, because expectations are minimum, are bare minimum, really. And by expectation, I don't mean like getting A in all courses. No, that's not important. Do some meaningful work. Go beyond what you learn. Obviously, learn perfectly in class, but go beyond that. Read a lot of books. Read a lot of papers. Do some incredible research. I'm sure many possibilities are just in front of you.
Yes, sir. Thank you for that.
Sure.
Thank you. And speaking of research, I am interested in researching, especially with like AI. So I will be emailing you about that.
Yeah, thanks, Bella. Yeah, definitely. As I said, I pressurized female students. underrepresented, and anytime I would be happy to help, and especially I would like to hear like motivation and yeah, I definitely encourage and looking forward for your email. Yeah, and also tell your other classmates, other students who you know. I mean, beyond this class, like there are. I all the time. I mean, not this year, but also like all the time. I'm looking forward for good students who are looking to do some incredible work.
Yes, sir.
Thanks for
Thank you.
discussion, and have a good evening.
Thanks, you too.
You too.
Take care.